Raghav, are you ready for?
Yeah, I'm ready.
Mhm.
Whenever you're ready, I'm ready.
Okay, yeah. Let's start. Good morning, everyone. This is the third day of the workshop. Uh, the first speaker is Raghav Jha from Permita Institute. He planned to visit APCTP in person, but unfortunately, because of the visa issue, he couldn't. But hopefully, in future, we can visit the APCTP in person. And today, he will give a talk on the new approach to continuous spin models in 2 and 3 dimensions. Yeah, please start.
Okay, so I would like to thank the organizers for inviting me to talk about some work I've been doing for the past couple of years. And this will be related to some continuous spin models. In fact, I'll also briefly talk about Potts model, which is not continuous spin model, but yeah, mostly about continuous spin models in 2 and 3 dimensions. And when I say dimension, it's like not a quantum, it's like 3 Euclidean dimensions, and I'll be dealing with the Lagrangian approach, partition function. Uh, so yeah, this is based on work given in these 2 papers mentioned here, and some ongoing work. Okay, so so the basic idea is that over the past 6 decades, we have had various renormalization schemes. Basically, the list here is not exhaustive, and some of the things have been analytical, for example, the work which is not mentioned here by Polchinski, exact RG and other things. But some of the major numerical advances have been mentioned in these bullet points, starting with Kadanoff's spin blocking RG transformations, leading to Wilson's RG, where he used his method to solve uh, the famous Kondo problem, impurity problem related to metals, using his prescription. Then the field was basically stagnant for 17 years until Stephen White in 92 came up with this method of DMRG, where you use basically the density matrices to carry out this process of renormalization, and is well suited to all 1D quantum systems, not necessarily methods by Wilson, which were good only for the impurity problems such as Kondo. Then after another 15 years in 2007, uh, there was this idea of using tensors to carry out the renormalization group procedure by Levin and Nave in their very famous paper. And this was later extended to something we called higher order TRG, and that is the acronym HOTRG, by Jha and al. In 2012. And these 2 methods are much more efficient than DMRG, but breaks down at criticality, similar to what happens to DMRG. And to deal with these critical systems, Giffre Vidal and his postdoc, Glenn, came up with this tensor network renormalization method called TNR, which improves the fixed point behavior and can be more useful to deal with systems which are at criticality. And this TNR is closely related to something we call MERA, which I'll briefly discuss in the coming slides. So this TNR, the idea of TNR is closely related to MERA. Okay. So this is a basic idea of what is happening with the RG methods. As I mentioned, this list is not complete, and if I have missed something, so I'm sorry for that. So let's go back to reading the old paper by Wilson from 1975, and I found this very nice. So in his review of modern physics paper, he mentions there are some aspects of renormalization group, and he mentioned that there is a 4th aspect of renormalization group theory, which is non-diagrammatic and which are solved numerically using a digital computer. To Wilson, this was the most exciting part of the renormalization group. And this was exciting because it made part of the theory that makes it possible to solve problems which are not reachable by Feynman diagrams or other methods, which was known at that time. And the Kondo problem has been solved by a non-diagrammatic computer method. So Wilson already in 1975 was using computers and numerical RG to do this. This has now only improved over the last 50 years or so, and we are now talking about tensor methods. We're going to higher dimensions and so on. So this all started in 75, and as he mentions later in the paragraph, that the Ising calculation is only a practice calculation. So whenever we want to develop a new algorithm in 2 or 3 dimensions, we always test it on the Ising model, at least in 2D, because the exact solution is known. In 3D, the solution is not known, but still is like you can benchmark your algorithms by testing it, your method, at least your favorite RG method, by applying it to Ising. So why do we want to really do RG, real space RG with tensors? There are several reasons. Some of them I have mentioned here. Basically, the advantage of tensors is that it provides an arena for studying lower dimensional critical and gap system faster than any other numerical method which is available today. For example, I'll show you a slide where I solve the 2D Ising model on a square lattice in 20 seconds, maybe 15 seconds on my laptop. So it's very efficient that way. So that is one motivation. The second is that formulation in terms of tensors can sometimes help us to study systems where the usual numerical methods such as Monte Carlo fail due to a sign problem. For example, another advantage in addition to this that we can probably study models with sign problem, in tensor networks, the partition function is directly accessible in the thermodynamic limit. And that is very useful in some of the problems we want to deal with, which is unlike Monte Carlo methods where you can only compute the expectation value of an observable. You never have the access to the partition function. So this is one advantage, that you have access to the partition function directly. The third interesting thing is that there are descriptions of using tensors to represent, for example, as I'll talk in the next couple of slides, to represent the ground state wave function of some spin model with some local Hamiltonian. It can be efficiently described in terms of matrix product states. I think there was a talk which already used this method to discuss the problem. So this is very fairly well known, matrix product states. So approximation of a wave function. And this can be used to study, say, for example, if I want to understand some real-time dynamics, such as scattering of particles in the field theory limit, we can use this matrix product state. So this is some work in progress, which I will not talk about today, but we are using matrix product states to study the Ising field theory. So Ising field theory is a 2-dimensional quantum field theory, which has a CFT description in some limit, and it was famously solved by Jamal-Duychikov in 1989. And we are working on this, and we are exploring the different limits of this theory in terms of matrix product states. So basically, we construct a Ising chain, spin chain, then write down basically the ground state wave function using MPS methods, approximation, and then you try to evolve that state and try to see some scattering by colliding 2 particles with some definite energy and momentum and so on. Another important aspect of tensor networks is that it is now known that tensors definitely play some role in understanding ADS-CFT, or more generally, I should say, in understanding how does the holography actually work. So the basic idea is that you have a quantum spin chain at the boundary, and as you evolve that state, you generate the additional dimension, which and that is what people have explored, and it's useful in trying to understand the properties of the bulk, basically get bulk physics from the entangled quantum state at the boundary, which can be described in terms of, say, MPS or MERA or something like that. So there are various facets of tensors which are useful, and that is why we are interested in studying this. Okay. So I mentioned before that the matrix product state is basically approximation of wave function. So tensors have both. Tensor networks approach belong to two categories, obviously: Lagrangian aspects and the Hamiltonian aspects. For example, when I say like Hamiltonian approaches, what I mean is approximating the ground state wave function and basically representing it as matrix product states, and then doing then computing the spectrum, for example, or other things which you want to compute, correlators and so on. And this is MPS is useful because MPS is the reduction is a reduction which takes us. So if I have a spin up or spin down, it has a local Hilbert space small d equal to 2, and the Hilbert space is of dimensionality 2 to the n. And obviously we cannot store that. Even like a state of 50 spins cannot be stored, or even less than that cannot be stored completely on the computer. So matrix product state is just a representation which grows linearly like n rather than as exponential or maybe some power of some local Hilbert space. So that is one advantage. When I talk about the Lagrangian aspect, what I mean is I write this partition function z, and the partition function is written like b to the h, or some action, as we can think about some action. And then we talk about the states which contribute, which have maximum contribution to the partition function. So tensor networks in the Lagrangian formulation is an approximation of the wave function, given the resources we have. Obviously, we cannot solve z completely in most of the cases, but we do the best possible approximation to the partition function. And that is what I'll be concerned in my talk. I will not talk about any wave functions. I'll just focus on the Lagrangian aspect, or I'll keep talking about the partition function or the action, for example. Just to give you a small note, one slide introduction to the notation, because there will be a lot of tensor diagrams coming in the coming slides. Any scalar can be represented as a blob without any legs. If there are two legs, it's a matrix. If it has one leg, it's a vector, and the tensor is represented by multi-index object. It's a multi-index object represented by n number of legs. If it is a rank n tensor, we can contract or combine the legs together. For example, in this case, we combine beta and gamma together. It becomes like the line thickness grows. That just means we are combining the indices together. We can contract the indices, and we can do all sort of things which we usually want to do. So this is a brief introduction. Matrix multiplication is just given by this. For example, if I want to multiply two matrices A and B, diagrammatically it can be written like this. So this is the basic diagrammatic notation we'll be using. So even though I will not talk about matrix product state, I just want to show you this figure, which is taken from this reference. And the figure is important because, for example, suppose psi is the actual wave function of, say, where I runs from 1 to n, and the Hilbert space is 2 to the n dimensional. This can be approximated by something which is given in the bottom, where you have a lot of matrices or this objects A, and then once we combine all these A, it gives me an approximation to the wave function. So instead of dealing with an exponentially large number of coefficients on the top one, we have something which grows only linearly with the i's, right? Because if I1 through I5, if it is going to On, then it's an order n parameter, not 2 to the n as in the description above. I also mentioned in one of the slides, which I will not discuss, but just wanted to show you this diagram because it's actually nice. And, yeah. Please.
On the previous slide, is A unique in the sense, what are the properties of A?
You choose A in such A. So, for example, in this case, which is the translationally invariant tensor, we just A is chosen such that when I multiply a bunch of A's together, I get the approximation to the wave function. So it's like some A. It might be same or different depending on the system.
Right. So how would you choose A? I mean, what is the input? Selecting A.
Yeah, so A is usually for some of the systems, like for example, there are some models like AKLT models. In that case, you can write these A exactly, but in most of the cases, you cannot write it down. So you start with some value, some A, and then you try to do some imaginary time evolution, and then you it's called ITEBD method, and then that gets you the more approximate values of A. I think that's how you compute this A's.
Nice. So somehow it is
Yeah.
related to the Hamiltonian of the system.
Yeah, of course, it depends. It depends on like what the Hamiltonian is. If the Hamiltonian is local, then only you can find these A's efficiently. If it is like Hamiltonian of some critical system, or say it's non-local Hamiltonian, then you can never find these efficient A's, and that is why matrix product states fail in those cases, because finding these A blobs is difficult in those cases.
Okay, thanks.
Okay. Yeah, so let's go to this idea of tensor and holography. I said that tensors represent, so what you see in this diagram below is the Mera basically. So it's Mera is some name for a tensor network. We don't need to know what it is. What it basically does is you have a quantum spin chain at the boundary, and then you coarse grain the system by introducing these blobs. So you can see that one of the blobs is four-legged, and one of the blobs is three-legged. For example, you start with two, and you, if it is from vector space V cross V to V cross V, it's known as distant angular. If it is from V cross V to V, as is the tensor which you see just after the first one, it just takes it in two legs and throws one leg. So that means that is the process of coarse graining. The input is two legs, but the output is one. So you read the diagram from the boundary towards inside. So what happens is, so the CFT is like this. So CFT is along the X direction, and the boundary is going along X direction. This is some time slice. So we take X, and then we take a constant time slice. And that is that was proposed to be dual to some ADS3 background, because ADS3 background has X, T, and Z. So it's a constant time slice, but the coarse graining gives you the Z direction basically, and that is the direction of the RG flow. So this is the relation between tensors and holography, in the sense that what it means that if I start from tensor description of the boundary state, boundary quantum spin chain, and I do the coarse graining, so basically that gives me the RG scale, which is the extra dimension which we need for holography. So this is the basic idea, and it's sometimes called as quantum renormalization group. And this is the basic fundamental on which any holography is based. So basic idea of holography is in fact quantum RG, and which is like pretty clear from this picture. If we can do this exactly, obviously it's exact quantum RG, but doing it exactly is not computationally possible, at least. So it's some sort of an approximation. Okay, so what I'll talk about is the standard TRG. Standard TRG is like as I said before, it's an approximation of this partition function. What we do is we start with some, if you want to do a two-dimensional classical statistical system, say for example, two-dimensional Ising model, we start with some initial tensor which has four legs, and then we do a decomposition of the initial tensor, and that is what you see in red and orange, green and blue. And how do we get to this red and orange? For example, you do a SVD as shown below. So you do an SVD, and then we can see that the two indices are combined. For example, we can combine the left and the top indices together and do a SVD, or we can combine the top and the right indices and do the SVD. And then this is an approximate sign, because sometimes we do SVD exactly, sometimes we do SVD but throw out the lower eigenvalues. In some sense, it's a truncated thing, truncated diagonalization, or truncated SVD, I should say. And that is what is shown here. So you start from this blue blob with four legs, and you eventually end up with four legs, as you can see, but with some approximation. So this is the basic fundamental of the TRG, which was given by Levin and Nave in 2007. But obviously, this doesn't work that well. So there have been several additional improvements over this. But the basic idea remains the same, is that you have a lattice which is represented, so you collect all these blue blobs together, you have something like a square lattice, and then you impose periodic boundary conditions, you get something like AN. AN just means that N steps of coarse graining have been performed. If in the first step of coarse graining, we just go to A1, so this is the first step of coarse graining. And if we contract all the legs of AN, it just means that we are getting the partition function. So contracting all the legs, like the opposite legs of AN, for example, left with right, top and bottom, we just get a number, which is the partition function. So if we carry out this process exactly, we get the exact partition function. If we throw out some singular values in this process, then we get an approximation to the wave function. So as I said, this was a basic TRG, but basic TRG doesn't seem to work in a lot of cases in which we do higher order TRG. Higher order is just a method of a better approximation of the better use of the singular value. So we use something called a higher order singular value decomposition, which is not, so what I showed you before was a first order, kind of a first order singular value decomposition. If we do a more sophisticated SVD, which is called higher order SVD, then the method becomes higher order TRG, which was given in this paper. This works much better for example, say two-dimensional classical statistical systems, or even three-dimensional systems. In fact, some of the research groups across the world have extended this method even to four-dimensional Ising model, but it's much more expensive, obviously, and the memory cost and everything grows very quickly with dimensionality. So certainly I can say that for 2 and 3, the results are pretty robust. And these methods are much less complex than the TNR methods or the MERA methods because it's computationally more feasible. So for example, some of the results I'll show now uses this method, which is the higher order TRG. Okay, so I promised a couple of slides before that I'm going to show you how I can solve 2D Ising model in 15 seconds. I'll just quickly pass through that. The exact solution is known, obviously. The free energy F as function of beta, where beta is inverse temperature, is given by this double integral. There's also a closed expression for this free energy, but it's some hypergeometric functions, which it's given by this double integral. And there is a continuous phase transition at this value of beta. So let's apply the tensor methods inspired by the Wilson's paragraph, which I showed you at the beginning of the slide, to see how does it work for Ising model test case. So it works perfectly fine. What you see on the left is the agreement of the free energy computed from the Ansager results and something I did on my laptop in 15 seconds with no magnetic field, obviously. So H is 0, and this is TRG. This should be higher order TRG, but it's also a version of TRG. So it just says TRG. And on the right, you see the specific heat, and you see the specific heat peaks around the same temperature, 0.4407, as we expect. Obviously, we can make it more accurate by going to a different, by doing the SVD in a better way, or keeping more singular values, and that amounts to increasing the bond dimension. But even for this simple case, it works pretty good. One thing which I just wanted to point out in the passing is that Ising model in 2 dimension with magnetic field is not solved. In fact, there's some mapping to a random graph, and it was considered in '86 by Kalakov and Bolatov, but it was not on a regular lattice. It was on a different graph, basically. So there's no solution for a regular lattice. But we can do the same thing with the tensors, and it takes few minutes as well. In fact, it is even simpler in some sense because there's no phase transition when H is non-zero. So it is well known that Ising model only has a phase transition in 2 dimensions when this field is 0. For any given finite value of field, at least the real value of magnetic field, there's no phase transition. So there have been some work related to the calculating the free energy of this Ising model for imaginary values of field, as you can see here. H is equal to I pi by 2 beta, but there's nothing known for real magnetic field. So F beta H for real H is not known. But for tensor description, it's simple because we can just compute this by doing the same process, and we get a free energy graph like this. So these are given for 4 different values of magnetic field. The magnetic field values are given below. The blobs or the hollow markers are the tensor results. The solid lines are some guess I have right at the moment for this expression, but obviously it's not unknown. So it seems to fit, but it seems to break at some point. So it does something. But these solid lines are not known in the literature. We don't know what it is. Okay, so now I go more closer to the title of my talk.
I have a question.
Yeah,
apart
sure.
from the partition function, can you get the critical exponents for the other operators in Ising?
Are you talking about the 2D Ising model?
Yeah. So when you do the 2D Ising model, there's the energy operator, and then there's the
For
the
2D
spin
Ising
operator.
model,
Can you get their dimensions from the TRG?
Yeah, for 2D, even for 2D O2 model, we have got some exponents. So for 2D, we can get the exponents, but in 3D, we cannot till at the moment. I'll talk about that in the later half of the talk.
Okay, thank you.
Yeah. So as was pointed by, I think it was David, I think, yeah. As it was pointed out, in 2 dimension, people have used TNR methods and even hot RG method to, for example, calculate, say, delta. How does the magnetization change with field? There's a critical exponent delta involved. How does the specific heat change with T minus TC? That's critical exponent alpha. So we can compute this critical exponents at least fairly accurately in 2 dimensions. And this 2D O2 model, people have looked at it, but there has not been a single computation of the critical exponent in any 3-dimensional system. And that is what I'm going to talk about. Why is that a problematic thing? And why do we really want to compute critical exponents in 3D? So let me talk about this paper I wrote in 2 years ago, roughly, where I studied 2D O2 model, which has a fairly simple Hamiltonian, and we just impose a symmetry breaking field. We can do the usual expansion using this Jacobi-Engler expansion, which is like a Fourier transform on some and well known. And this gives you an expression in terms of Bessel's function, and then integrating over the angles and doing all those things, you can get the initial tensor, which is given by product of 4 Bessel function when field is 0, and product of 5 Bessel's function when the field is non-zero. So if I put h equal to 0, it just imposes the condition that this should be a delta function. So basically, when h is equal to 0, I plus k always has to equal j plus L. And that is just the conservation of U1 charges entering at any given particular vertex. So the left plus top should be equal to right plus bottom. So that just said, yeah. Please.
That reference number points to another paper called Bootstrapping Matrix Quantum Mechanics by some other people, I'm afraid.
Oh, shit. Oh, okay, sorry. I'm sorry.
Maybe to 2004-06314 or something, your paper.
Yeah, I'm sorry. This paper is not my paper, actually. This is embarrassing, but okay. I also work on matrix bootstrap. So this reference is a matrix bootstrap reference. Yeah, but you can find, if you're interested, you can find my paper easily. So I just leave that. Sorry, but yeah, you're right. So the basic idea is that the conservation of U1 charges gives you that delta function, and then we can, so the delta function for h equal to 0 ensures conservation of U1 charges. And this model is interesting, at least to people who do these sort of spin model tensors, because this has a famous BKT transition, which corresponds to unbinding of vortex pairs, as is well known for so many years. Note that in 2 dimension, because of this Mermin-Wagner-Coleman theorem, there cannot be, one might not expect a phase transition, but BKT is a special case of a phase transition, because this is a phase transition of infinite order, basically, in the sense of n-phase classification. And I say infinite order because if I compute the free energy, as I'll show you in the next slide, using tensor methods, all the derivatives of the free energy is continuous. None of the derivatives of free energy is discontinuous, and we cannot see any signal of phase transition in the free energy. We have to do some fancy, sophisticated methods to get the phase transition, and I'll show you what we do. So there's this free energy given on the left. I give it for 3 different values of h equals 0, 0.1, 0.5. And on the right, I show you how we compute that free energy on the using the tensors. So for tensors, if the orange is equal to blue, then it computes the partition function. The numerator is the same structure as denominator. If I insert a orange here, like is given here, it computes some observable, for example, magnetization. If I insert a red tensor instead of orange, it will compute some observable corresponding to the red tensor. So that is how we compute the partition function or any observable in the tensor. On the numerator, you take the impure tensor and sandwich it with neighboring partition function tensor and just divide it by the partition function, which is given here. This is just z, and this is O times z, the usual way of computing the expectation values. So what do we do if we cannot compute the phase, look at the phase transition from the free energy or something? What we compute is that we compute the magnetization for small symmetry breaking fields. And if we do that for sufficiently small values of symmetry breaking fields, we get a plot like this: 1 e minus 4 through 1 e minus 8. And we take and we read the specific heat from the susceptibility. So for on the right, you see that the peak of the susceptibility corresponding to some very small magnetic field is given by this. And then you do it for very small values of magnetic field. You do a precision calculation and you extrapolate to the h equal to 0 limit, and we get the result which is mentioned in this table. So this system has been studied using Monte Carlo for the first 21 years, and recently, first 21 years. And then in the last 7 to 10 years, there have been 3 studies. Higher order TRG computed this number, then uniform MPS was this number, and doing higher order TRG with some algorithmic advancement, I computed it to be this number. So it's like a agreement to the Monte Carlo results from 2012, and this is the most precise agreement of the critical temperature on square lattice. I think there's, okay. Okay, yes, so I did not look at critical exponents in this paper because there was some other algorithmic improvements that had to be made, but there was soon after this paper, the other group followed up and they computed the critical exponent delta and so on, and they got fairly good numbers. But they used more powerful supercomputer rather than my laptop, as was done in this case. Okay, so we talked about 2D O2 model, but there is another interesting model which people have been looking into, is that we can modify this 2D O2 model by adding a term which now depends on, so this is not two negatives, it's just single negative, there is a typo here, but we add another term which is like cos p times theta I minus theta j. Obviously, when p equal to 1, we can say that the usual XY model, but what happens if we consider p greater or equal to 2? So this is some work in progress. These models are known as generalized XY models. These are more interesting in the sense that in addition to the integer vortices and anti-vortices you have in characteristic of in XY model, you now can have half integer vortices, and the phase structure is much more richer because now you have a phase transition between the disordered and the half integer phase, disordered and the full integer phase. So it's much more complicated and much more interesting. So that is what we are looking into right now. So the rough diagram, for example, is given by this T delta plane. Obviously, when delta equal to 1, for example, this is delta 1 minus delta. If delta equal to 1, this is the only term that survives. And if delta equal to 0, then only this term survives. So it's like 2 different limits. So delta equal to 1 is BKT transition. There's just a single transition, which is well known from integer vortex pair to the disordered phase. But as we decrease delta, we pass through this multi-critical point where different transition lines are meeting. So the dashed lines you see are the BKT lines. The solid line is the Ising type transition. So if you start from delta equal to 0, go to the multi-critical delta MC. You follow the transition is like Ising type, and then suddenly on the left, and then it becomes BKT like. For example, half BKT like or full BKT like. It's half if it is going from half IVP to disordered, or if it is going from integer vortex to BKT, it's a usual BKT. So this is a cartoon of the conjecture phase diagram. And our idea is to zoom in on this multi-critical point and explore this phase diagram in more detail. So this is some of the preliminary results I have by running on my laptop. We see a peak, for example, this is for delta equal to 0.2. We see a peak around 0.44. So it's just corresponding to this somewhere along, maybe it's along this line or some transition along this. Obviously, if I go to higher values of T in this case, I will encounter the second transition, which is half BKT transition, which is from half IVP to the disordered. The one I show up here is from integer vortex pair to half integer vortex pair. Okay, so that is some work in progress, should be published hopefully soon. Now, I want to go to 3 dimensions because why not? Let's just see what are the problems. So of course, there are a lot of problems, and that's why we don't have much results in 3D. The problems, some of the problems are the errors which we accumulate as we do the coarse grading renders any reliable RGE procedure inefficient. The second reason is that the growth of entanglement, which comes from cutting down the bond using a finite bond dimension and other things, it just grows, and if this is not removed by some well-defined procedure, one will never reproduce the correct behavior. And the third problem is that the computational time is much more expensive, like becomes much higher if you go to D equal to 3 rather than being at D equal to 2. So it becomes, for example, the time scales like D to the 11 in 3D. And also the memory costs increase. So the intensive network computation, there's computational cost like CPU time and the memory. So both of them increase, and it becomes really hard to tackle it. I've shown a small description of why that is true by drawing 4 rank 6 tensors. So you see in yellow rank 6 tensor, because we are in 3D, we have a rank 6 tensor. We combine all of them together and do the usual hot RG procedure, and we see that and we see that there are so many indices that the SVD cost becomes pretty large, and to compute these projectors UX and UI, it really takes time, and this is hard. This is one of the reasons it is hard. But there was some so why do we want to really study 3D O2 model? The reason I want to study is that, say, how close we can get to 2 other methods which are known today, which is Monte Carlo method and conformal bootstrap. So we really want to study some spin model, starting with obviously the simplest O2 model, or even for Ising model. But let's start with O2 model, the simplest continuous spin model in 3D, and see how well we can do, how far we can reach using tensors approximation, real space RG. So that was the motivation. So we could never do it efficiently using the hot RG, but there was some progress in 2019 made by Kado and other people. There are some other algorithms, but I will mostly focus on this triad decomposition. So the basic idea of this paper was the rank 6 tensor cannot be carried all the way through all the process we want to do. For example, SVD. We break this rank 6 tensor into 4 tensors of rank 3 each. So for example, one with, as given here, A, B, C, D. And each of these have 3, are rank 3 and known as triads. So that is why this method is triads method. And then instead of dealing with T head on, you just keep carrying A, B, C, D and do the renormalization group method. So that was the basic idea. So how do we do that? The first step is to break this 6 tensor as is shown in the step A. And then in step B1, you combine 2 of these together and do the efficient contraction so that you get a matrix, obviously. And matrix has 2 indices, x1 cross x2, comma x3 cross x4. So you have a matrix, and then you do the SVD of that matrix. You compute the projectors, U dagger, V dagger, and then you do the contraction with the projectors, and you end up at something which is given after step E, and that gives you this new tensor and then you do the same thing along the z direction. So once we do this process, which is shown here 3 times, we have effectively done the coarse graining along in the xy plane, yz plane, and xz plane, and that forms one step of coarse graining, and then we get back to the same tensors. Obviously, we get a prime, b prime, c prime, and d prime, where it's just one step of coarse graining. And then you do this sufficiently number of times, and you hope that you converge to the right, correct fixed point behavior, so that you can reproduce, you can do get out the physics which you want. So 3D spin models with tensors, what have been done till now? Ising model was well studied, but critical exponents have not been yet computed even for Ising model. We studied O2 model with some of the collaborators, and then I looked at this Q state POTS model, also in 3D using these tensor methods, especially the triad method. Okay. So let me just briefly mention 3D Q state POTS model, because it's not a continuous model, but it's interesting in the sense that we have some new results, which I would like to talk about. So basically what we can do, we can take the Ising model, but say, okay, let's say the local Hilbert space is not 2-dimensional, but Q-dimensional. So for example, it can be 1 to 3, 1 to 3, 4, and so on. Q can be any number. So this problem was explored using Monte Carlo for a Q ranging from 3 to 10. However, it was soon observed that Monte Carlo becomes pretty difficult, even already at Q equal to 10. I also want to note that the phase transitions for any Q greater than 2 is first order, and obviously for Ising model, it's continuous phase transition. So the critical Q where this changes is some value between 2 and 3. So for all of these purposes, it's the first order phase transition we are looking at. And we use some tensor network methods, which I just explained, to look at Q, which is between 10 and 20. So there's no result available in the literature, and I thought, why not we just look into this, and we just found it. The real motivation was to understand the fact that how the critical temperature varies with this Q. If we talk about 2-dimensional pot state model, the critical the expression is well known, and it was solved by Baxter long back, and you can find it in his famous textbook, Exactly Solvable Models. But in 3D, nothing is known. For example, if I ask the same thing in 3D, we don't know how TC as a function of Q looks like. So we had some results from Monte Carlo, which is on the left side, and then the shaded region are some results I got in this paper. But it still, I tried to find an expression, reasonable expression, like get using some facts of 2-dimensional, but it seems like it's not easy to do. And obviously it's a expression, it's a long outstanding problem in statistical physics, at least, to find this expression for 3D Q state POTS model. But maybe this data, and we can, if we can, there might be some possibility. So these are some new numerical results I have. Okay, so this model, now I move to the 3D O2 model after explaining this POTS model briefly. So what do we want to eventually compare? For example, in Bootstrap, one studied the scaling dimension, as was pointed before, of these chart zero scalar operators. For example, we can compute delta S, which is the standard thing people in conformal Bootstrap compute, and it is related to some critical exponent mu as given here, and it's also related to alpha as 2 minus dimensionality, which is 3 in this case. So 2 minus 3 times mu is alpha, and alpha is just the exponent related to the divergence of like to the specific heat, and nu is related to the correlation length. Just to remind you about those exponents. So we want to eventually get to a point where we want to compute these nu and alpha using tensor network methods. And if we can compute this nu, we can see how close we are to conformal Bootstrap by using this relation. So the method we use, at least the triad method we use, was good enough, I think, to study thermodynamical observables like free energy, specific heat, determining the transition. But it seems that that algorithm really breaks around critical point, and obviously the determination of the temperature cannot be done to say 5 decimal places or 6 decimal places, and obviously that eventually means that computing the operators doesn't seem to be that promising at the moment. Maybe if there is some better algorithm we use or use some advanced enhancement of the triad algorithms, we might be able to do these calculations in the future. But right now we can just compute thermodynamic observables and critical temperature at best. So how do we do this? The action for this model is simply given by this expression given here, similar to what we saw for 2D O2 model, just that now we are in 3 dimension. The tensors is exactly the same, just that the number of Bessel's function have increases because every index has to carry a Bessel function weight, and that is the initial tensor which we have, which is rank 6. And we take this tensor, we compute the energy. For example, in this case, I show the energy obtained from the tensor network computations and the energy obtained using Monte Carlo methods. And we see that there's a very good agreement. On the right, I show the peak of specific heat, which is obtained from 2 different methods, hot RG and TTRG method. TTRG is the triad approximation, which I discussed before. And we see a reasonably good agreement, but obviously as we go.
Hello, question.
Yeah.
On the previous slide, so
On the
so there are these Bessel function weights. So usually Bessel functions appear when there is a cylindrical symmetry in the system. So I'm wondering, whether there is something there. I mean, some kind of symmetry.
Yeah, basically the Bessel function here is just coming from the Fourier expansion. Basically, when you do the expansion of these angles in terms of this, so you do. So basically, I want to if you rewrite exponential of a cos theta. If you do an expansion and you want to rewrite that, it's always in terms of Bessel function. So there is some sort of a I don't know how it is related to the cylindrical symmetry, because theta can. It's just a Bessel function, not like the cylindrical symmetry leads to a Bessel function, but Bessel function can come up from other ways also. In this case, it's coming from a Fourier expansion or character expansion. It's something which we also see.
So I was just curious.
Yeah, for example, Bessel function you also see in Gauss-Witten-Wardia model, but Gauss-Witten-Wardia model has no cylindrical symmetry.
Okay.
Like, there's nothing symmetrical about that. Yeah, so I think it's just from the fact that we are doing some character expansion or some Fourier decomposition, as a lot of people like to say. Another word for character expansion. Okay. Yes. So, but obviously this process becomes a little harder when we go tune very close to the critical inverse temperature, and that is obviously the well-known problems in higher dimensions. And so one has to come up with better methods if you want to go to more like higher level of precision. So we compute the magnetization, and you can do it for different values of field by inserting an impure tensor, as I mentioned before, and we get this slow as we lower the value of magnetic field, we see that it's clear that the peak is like going towards expected result, which is 0.45 with some error. So that's good. We have 2 distinct way of getting the same thing, and they're both agreeing with each other. So that means tensor network setup is completely fine. But now we can go a step ahead. Now we can go, instead of matching to Monte Carlo, we can go further than Monte Carlo by introducing a chemical potential. If we introduce a chemical potential, we have this extra term which you see in the action here, which corresponds to a given specific dimension direction. For example, just pick up one specific direction, nu equal to 0, and you sandwich this, put in this chemical potential term. Obviously, the action becomes imaginary, cannot do Monte Carlo, but tensor networks don't have any problem as per se. And then that is one of the motivations. And this also leads us to the very speculative ambition of doing, for example, someday doing finite density QCD, or doing some gauge theory with theta term where we cannot do usual Monte Carlo. So I'll just talk about the chemical potential introduction in 3D O2 model and see what we get. So in the 3D O2 model, what we looked apart from looking at the magnetization, as I said before, and the energy in the specific heat, we looked at what we call this number density. So, for example, if we consider finite values of mu, we can compute the number density, which is just given by the partition function with respect to mu. And one of the interesting things is that, for example, if I take a gapped system, say for beta, like little away from beta c, then this rho remains 0 until some critical chemical potential. And this phenomena is known as silver blaze phenomena, based on some novel written by Sherlock Holmes more than 100 years ago. And this is known as silver blaze because what this phenomena says is that, similar to what happens in the Sherlock Holmes story, rho is 0 because the z is independent of mu until some point. So even though mu is in the action, basically the action doesn't see the chemical potential unless we cross this threshold of mu c. And this, it must be noted that this is proportional to mass gap. And the basic idea about this is that if you are at chemical potential less than the mass gap, no particle can be excited, and hence the particle number density remains 0, and z is independent of chemical potential. And we see this in the plot on the left. For example, as we go from 0.42 to 0.46, I remind you that the critical temperature is around 0.45 plus something. So as we go from 0.42, the gap is decreasing because mu c is decreasing. And suddenly, once we get to that transition region, the gap completely vanishes. So there's no mu for which rho is 0, just rises. And this is also seen in a, so on the left, we have a symmetric lattice of some size, say for example, 1024 cubes. On the right side, we have a lattice which is asymmetric lattice, which with different number of sites along the one of the direction in which we put the chemical potential. And we see that if NT is much smaller than NS, basically there are some finite temperature effects. And then rho is never 0, it just rises linearly with mu. But as we go to symmetric lattices and go to this symmetric lattices, and there is no well-defined, like at least we see that it is consistent with some silver blaze phenomena. So as we take NT higher, we get to the symmetric lattice on the left side. So we reproduce this silver blaze phenomena using tensor network methods, and this was a nice calculation because this was the first time any group tried to do this in 3D. This has been done for some 2D gauge theories and 2D spin models probably, but not in 3D. So 3D also we see some agreement using the tensor method. So it seems like for these problems it seems to work. So let me just summarize since I have only 5-7 minutes left. So tensor network methods have potential to assist in various interesting problems in physics. On one hand, it can efficiently reproduce the ground state of several quantum systems with matrix product states or projected entanglement pair states, which calls PEPs. It can also, on the other hand, describe some real space RG transformations in various dimensions and can help us in better understanding spin models numerically, or complex action systems, or in fact, gauge theories. So I didn't talk about that, but we also did some work with Simon and other people at Syracuse when I was a PhD student there. We did SU2 gauge theory in 2 dimensions, and that we did using tensors. So it's also U1 gauge theories with theta term have been studied, SU2 in 2 dimensions have been studied. In fact, I don't know, Nishimura also studied a matrix model using this tensor network. So these are interesting approaches, and it is indeed a very exciting approach to Wilson's 4th aspect of RG. And as Wilson said in 1975, it is still as exciting. I would say it is even more exciting with tensor methods and with quantum computing and other things coming in the future and better tensor algorithms. So with that, I'll end, and thank you for listening.
Yeah, thank you very much for a very clear talk. Now, please ask a question.
Can I ask a question?
Yeah, sure.
Well, I have a question about your calculation of the critical point of the two-state clock. Sorry, Potts model. Can you?
Okay.
Could you go back the slide?
Yes, I can. Yeah, it's there.
This one. Thank you. So, well, this calculation is done by the in the 3 dimensions, right?
Correct. Yeah.
So in that, so the first question is, how did you determine these location of the critical points?
Okay, yeah. So the way I determine the location of the critical temperature was looking at the behavior of the energy. So, for example, as I said before, it's a first order transition, right? So first order transitions are usually accompanied by some latent heat. So if you go close to the critical temperature and you just follow how the energy is changing, you'll see that energy follows some definite shape. So I used some ansatz and found out the latent heat, and that is how we found out the critical temperature. So you find the point where the slope of the profile of the energy change increases is more steep. So you do some sigmoid like a function, fit function, and then you compute the point of maximum steepness, and that is the point where the transition is, because that is where you can compute the latent heat and the transition happens.
I see. So, and this calculation is done by your triad method, right?
That's correct. This is completely the triad method.
So in that case, you can, as another choice, I think you can also calculate or see the degeneracy of the largest eigenvalues.
That's true. And I looked at the degeneracy. Yeah, I looked at the degeneracies already using that method.
And that way of determination of the critical point gives the similar result or not?
Yes, it should give the similar result.
Yes,
but but the thing is that I could not compute that observable computing corresponding to the degeneracy very precisely. So the triad method could not compute that degeneracy very precisely. So I did not pursue that direction. But I agree that finding calculating that spectrum degeneracy is a good. I looked at it, but I didn't succeed, I should say that. And that is why I determined using the energy, because that was much more cleaner. The data was much more cleaner and it was much more robust, while the other thing was not.
Okay, so it seems to me that with the use of the triad method, I think the calculation of the degeneracy becomes much more difficult in the large Q region, right?
Exactly. That is my thinking at the moment. I think the triad approximation somehow. So the determination of that spectrum degeneracy is very closely related to the correct fixed point behavior. Because if you're not getting the correct fixed point behavior, that completely ruins that calculation of that observable. And I think somehow the approximation made in triad method is good for free energy, internal energy, specific heat, and things like that. But somehow it becomes a little tricky for the things like degeneracy or other things.
Okay. So I see.
Yes. So I think there is still, if we can compute those things using any tensor algorithm, I think it's a very good direction. And that will be a nice computation. Yeah, but I couldn't do that using triad.
Okay.
Yeah,
thank you so much.
Yeah, thank you for your question. Yeah.
Yeah, thanks for a nice talk. So I have a very simple and generic question. Do you think these methods would work for disordered systems and glasses in particular?
Sorry, let me just repeat your question. You are asking whether this method will work for spin glass systems or something like that, disordered system? I don't know whether people have looked into. I don't think there are a lot of at least I don't know of. Yeah, it might not be okay. I don't know. I don't know much about spin glass and things, but I think the basic fact is that somehow these tensor methods have not been much applied to those, because I think, do you have translational symmetry and other things in those systems. I think they're impure systems, right? It's a little harder to do. Like, if you lose that, if you lose the translational symmetry, a lot of tensor computation becomes a little harder, because the fact that it's like if you just put a little impure tensor during your course grading, it becomes a little more complicated. I think the errors accumulation grow. Maybe it's possible to do in 2D, but I don't know whether people have. I don't know much about that. Sorry.
No. Okay. Thanks. I have a question. So here you mentioned the gauge theory, and how do you treat this gauge in this tensor network? You probably
So
particular freedom, but
so right now, how we are doing this, at least for the U1 gauge theory, how groups have done it for U1 gauge theory, and we did for SU2 gauge theory. Like we do the character expansion, like a strong coupling expansion, which is well known in the lattice field theory literature. So you do a strong coupling expansion, but you have to truncate over some irreducible representation of the gauge group. So for example, you start with the trivial representation, then you go to the fundamental, adjoint, and so on. So you keep some number of representations, and then you start with this strong coupling expansion method, and then you do the coarse graining. So it's not like the usual standard strong coupling, because in that you don't do the coarse graining. In this, you start with that, but you do a coarse graining, and you hope that you flow along the RG to produce the correct behavior. But definitely it gets harder it's a little harder to take the continuum limit for the gauge theories, I think, because the character expansion has some problems when the it's not the best starting point, I think, for like getting so the tensor has some problem with truncation and other things when beta becomes very large. Beta is 1 over g squared. So for small beta it works fine if you truncate over the reps of gauge group. I think that's how we so it's just a character expansion of the in the gauge theory, basically. That's what we do.
Okay, thank you. Is there any other question? If not, let's thank the speaker again.
Thank you.
We will meet in 15 minutes.